So let me continue with this. I am a little off my schedule, but I'm going to cut on certain parts, hopefully, to make it up. So let's at least discuss these equations, which we call the Rayleigh line and the Hugoniot. And the first case I want to is to consider the case, I think that's what's coming up, when Q is equal to 0, namely no heat release. So what solution do you expect in an inert mixture? In other words, what kind of wave can you find in an inert mixture in which the gas is propagating from one end to another and the properties are changing across the wave? And so, so that's not what I had. Okay, so sorry, we will get to that one in a little bit. What then I wanted to do is to graph these two curves. Remember that in other words, I'm going to talk about the case Q equal to 0, but it's going to come later. So remember I said that this is a straight line with a negative slope. So we're going to graph it later. But this expression, which is a function P as a function of V, which is what we want to plot in this diagram, it's called the Hugoniot. It turned out that that is exactly a hyperbola. In fact, it's a rectangular hyperbola. And this is what it looks like. These are the different Hugoniot for different value of Q. Okay? As you increase Q, they move further away from that point. Note that there is only one curve, okay? One curve which corresponds to Q equal to 0 that passed through the initial point, 1, 1. In fact, that you can see from the equation itself, right? When Q equal to 0, if you substitute V equal to 1, you get P equal to 1. So the Hugoniot with no heat release go through the initial point. The Rayleigh line always go through the initial point, because if you substitute P equal to 1, it's equal to mu V minus 1. So P equal to 1, V equal to 1 satisfy this equation, right? So the Rayleigh line is always a straight line that will start at this point, and being a negative slope, it will go either this way or that way. But it can never go this way. It can never go a positive slope, right? Because of that, there is an entire region where no solutions are possible. This is the one I blocked here, right? The Rayleigh line is always go through 1, 1 and has a negative slope. So it will start here and it will have a negative slope. So it can be either in this direction or in this direction. So solution can only be found only in this strip or in this strip, okay? Furthermore, from this previous diagram, what we see is that there are two asymptotes. In other words, as V approach this value, which is positive, and it's given by gamma minus 1 over gamma plus 1, which is a positive quantity clearly, P goes to infinity. So all the hyperbolas asymptote to this line. They also all asymptote to this line, but unfortunately, not unfortunately, but this is a negative P. So there are many states here which are clearly not physical and irrelevant, okay, where P is negative. So the only P which are of importance is from this point to the left. In fact, this is going to come back again. So here it is. So the only relevant P is from this point, right, to the point where it intersects the axis, or from this point to this point, and so on. But and the possible solution on this end are from 1 up to infinity with P, but V, of course, is limited by the asymptote. So there is a range of P and V where solution can be obtained. Now, the solution obtained in this region are called detonation, and those obtained in this region are called deflagration, based on their properties, which we are going to examine. Now, the name comes because of the property of the wave. Here is the case Q equal to 0 that I said earlier that I want to analyze. So when Q equal to 0, both the Rayleigh line and the Hugoniot pass through the initial state 1, 1. And so you start at this state, and then there's only one possible solution in this direction and one possible solution in this direction, right? Because any curve that starts here, a straight line, can intersect the Hugoniot only once, clearly. Now, this is a state in which the pressure increases significantly. The v, the velocity relative to the wave, decreases, but what it means is that the density increases. So this is a state in which the pressure increases, the density increases, and as a result of the equation of state, also the temperature increase. And it's a shock wave. It's a regular shock wave, normal shock wave. The other possible state here will be one that P decreases, will be something like a rarefaction wave rather than a compression wave, but based on the second law of thermodynamics is not a possible state because it turned out that it violates the second law. So even though there is a possible solution here, physically it's not possible. Okay? So in the case of Q equal to 0, there's only one solution, one possible wave, which is the normal shock wave. When Q is positive, however, you see that every Rayleigh line or every straight line that starts at 1, 1 can intersect the Hugoniot twice. Of course, as the slope decreases, right, then there is a possibility of only one intersection. That's the case where the dash curve is just, which is the Rayleigh line, is just tangent to the Hugoniot. And for lower values, there is no solution. Similarly, on this end, where you have deflagration, then again you have two possible solutions, or one when the Rayleigh line is tangent to the Hugoniot, and when you increase the slope further, there will be no more solution. Now, the two states are usually referred to as strong and weak, so that's a strong and weak detonation, and this is strong and weak deflagration. And the state that is tangent is known as the Chapman-Jouguet, after Chapman and Jouguet, who discussed that first. So this is in a way summarized here. For detonation, we have seen that there is a minimum value of mu, right? And as a consequence, a minimum wave speed corresponding to the Chapman-Jouguet detonation. And when mu is above the mu Chapman-Jouguet, there are two solutions, the strong and weak detonation. Passing through a detonation wave, as you can see from here, of course, the pressure increase, the density increase, and V decreases, right? So this is what's summarized here. At deflagration, there is a maximum value of mu, which is the largest slope we've seen on the other side, right? And as a consequence, a maximum wave speed, and the maximum wave speed corresponds again to the case where the two are tangent to each other, and that's the Chapman-Jouguet deflagration. For mu below the Chapman-Jouguet, there are two solutions, a weak and a strong deflagration. And passing through a deflagration wave, the pressure decrease, the density, the velocity increase, and the density decrease, right? So now, the deflagration are what we usually refer to flames, and detonations are detonations, and we are going to talk a little bit about the different characteristics of the two that based on their properties. So first of all, there is a quick calculation here, but I'm not going to go through the calculation. Remember that every state here, which I identify as a possible solution, is one that satisfies both equations, the Rayleigh line and the Hugoniot, which means that it satisfies mass, momentum, and energy conservation. But knowing these, from this relation, the only thing we can obtain is the end state given the initial state. What we cannot calculate from these two relations is the wave speed, which is V naught. And I have indicated for a given mu, you can find the end state, right? However, for a Chapman-Jouguet, detonation or deflagration for a Chapman-Jouguet state, you have one extra condition, which is that the slope of the two curves is equal to each other. That additional piece of information allows you to calculate the speed as well. So the Chapman-Jouguet waves, the speed can be calculated directly from this relation. And this is what essentially is shown here. So this is the Rayleigh line, the Hugoniot, and if you calculate the derivative of the Rayleigh line, the derivative of the Hugoniot, and you equate them, then you end up with some relation that tells you something about, first of all, well, it should be before that, no? It's after. Okay, it tells you something about the Chapman-Jouguet, first of all, about the properties that what you find is that the downstream Mach number of the Chapman-Jouguet wave is always sonic. Okay, so the Mach number is 1, so the velocity is always sonic. That's one condition. And then the second thing that you find is the wave speed, but also not only the wave speed, you can calculate all the properties like in every other case. Note, by the way, that's why I'm not moving forward, I just want to show you that to calculate the end state, it's very simple because if you evaluate these two relations, after you eliminate, say, P from here, you're going to get this term on the left-hand side, and when you multiply through, you get a quadratic equation. So essentially, you get a quadratic equation that gives you immediately the two possibilities, the detonation and the deflagration in one shot. And so this is some of the algebra that you get. The plus and minus correspond to detonation, deflagration, and this is the upstream Mach number in general for both deflagration and detonation. Now, I don't know why there is a place here where I should have had the value for Chapman-Jouguet, and I don't see it. But it probably will come. So anyway, the summary, and I again don't want to go through all these details, is that one find, here it is. So here is the upstream Mach number, m naught, which of course gives you also the velocity upstream, which is v naught. So it tells you the velocity of the wave. So what you find, the plus corresponds to detonation, the minus to deflagration. So what you obtain is that detonation are supersonic waves because m naught is going to be clearly bigger than 1, right? You have 1 plus the same quantity that you have here, so it's always bigger than 1. And the negative is going to be always less than 1 because you subtract the quantity which is in here, same quantity basically. And so m naught for deflagration is of course subsonic, and it's less than 1. And then you can find other properties which are based on analyzing these different cases, and all these properties are summarized in the one in those graph that I will get to. But before this, I want to also that you pay attention to this one here, which I have alluded to before for a special case. Essentially, what I want to address here is what is the fluid particle velocity for each of these two cases. And the fluid particle velocity, remember, u is v minus the wave speed. The wave speed was minus v naught. So it's v minus v naught, and when v is less than v naught, which is in detonation, then u is negative. And so u negative means that the gas is moving in the negative direction, the same direction as the wave. So here is a time displacement or xt diagram. If this is the wave, the detonation wave, that's the front, so it's moving at some speed, which is the slope of this line, okay? Then if you take a particle which is sitting at this position at time t equal to 0, well, the wave didn't reach it yet, didn't reach that point, and so that point remains with velocity 0. It doesn't move, it's there at the same position until the wave hits it, and then it is compressed and it's followed the the wave, right? So it followed the wave. In a deflagration, on the other hand, V minus V naught is positive, so U is positive, and so as the wave is moving to the left, but the burn gas is moving to the right. So it expands and moves away from the flame, okay? So this is that. Just a general comment which is important. The Rankine-Hugoniot analysis provides for given condition the state of the gas downstream, but does not determine, except for the Chapman-Jouguet wave, the wave speed. So this is still something that we need to determine based on the internal structure of the wave. So we're going to do that for a flame and for a detonation wave. The possible existence of a final state based on the analysis that we have just gone through does not guarantee the existence of a solution. All what we have done is that we have said, well, there is one equilibrium, another equilibrium. But those two equilibria need to be connected, and they need to be connected via the conservation law. Namely, we have to solve the differential equation that connect one state to another. We didn't do that. We only analyze what possible state can exist. And so one needs to ensure that the initial and final states are connected smoothly to a solution of the differential equation. At least we're going to show that for flames. But in general, that point can preclude some possible solution from being physically realistic because they cannot be connected from one state to another. So for example, we have seen that there is weak and strong deflagration, and the strong deflagration is not usually a possible state. One can eliminate it on that basis. But that's not the same for detonation because both are in principle possible, but we are going to discuss that in a little later. So here is a summary of the difference between the properties of deflagrations and detonations. Deflagration are expansion waves that propagate subsonically. So the Mach number is less than 1. The burn gas behind the front expand and accelerate away from the front. In a frame attached to the wave, the downstream flow beyond the Chapman-Jouguet wave is sonic. For weak deflagration, the M infinity is less than 1, and for strong deflagration is bigger than 1. Wave structure, that's the point I just made a minute ago. Wave structure consideration forbid strong deflagration. There is no structure that connects the burn and the unburned state. So really, in the deflagration end, there is only one possible solution, and that's weak deflagration. That's what we call flames, essentially. There is a unique solution for weak deflagration, giving a definite wave speed for each gas mixture. This is what we know as the laminar flame speed. In other words, there is, for a given mixture, there is a property that it's a laminar flame speed, which is the speed that such a wave would propagate, and depend on simply the properties of that mixture. And just to give some numbers, weak deflagration of flames travel typically in a range of 10 to 100 centimeters per second. So 1 meter per second, it's quite fast. Flame, it's usually hydrogen-oxygen flame, can propagate approximately that speed. The ratio of the pressure at the end state to the initial state is very small. Remember, the curve is rather shallow when it meets, right, the straight line, the Rayleigh line, when it meets the Hugoniot. And so the change in pressure is quite small. It's a simplification that we will discuss later on, and it's related to the so-called low Mach number approximation. The temperature ratio, which is also the inverse of the density ratio, is about 6, and that's typical for deflagration. Detonation, on the other hand, are compression waves that propagate supersonically. M naught is bigger than 1. The wave retards the burn gas that are compressed and move in the same direction. In a frame attached to the wave, the downstream flow beyond the Chapman-Jouguet wave is sonic, which is true for both Chapman-Jouguet, but for weak detonation is supersonic, for strong detonation is subsonic. A strong detonation can be produced usually by driving a piston at an appropriate speed into a mixture, and that determine in a way the propagation speed. Freely detonation propagate usually at the Chapman-Jouguet speed. And that's something we will discuss when we get to that lecture. There is only one wave speed at which a weak detonation can propagate, but weak detonations are seldom observed. You need very special mixture to observe them, and so we will typically not discuss that. So the structure that we will discuss, which is primarily so-called the ZND, the Zeldovich-Doering von Neumann-Doering ZND, Zeldovich-Neumann-Doering structure will be discussed, which is essentially for strong detonation. And to have an idea of self-sustained detonation, which are Chapman-Jouguet, for example, in hydrogen air mixture, the propagation speed is something of the order of 2,000 to 3,000 meters per second, so it's very, very fast, right? The pressure increase is about 20 compared to the initial, 20 times the initial pressure. The temperature ratio is about 10, and the density ratio is about 2. So it's our typical numbers. Okay, so there are a few comments here made. I think this is the last slide. Let's make it, oops. Sorry. Press the wrong button here. Okay, so this is the one, yeah. So, what does it say? So, deflagration are subsonic waves, so the disturbances behind the wave can propagate ahead and affect the state of the unburned gas before the arrival of the wave. In other words, you have what we call upstream influence. The expansion of the product can therefore cause a displacement of the reactant, so that the wave can move faster than the flame speed under such condition. Now, in unconfined obstacle-free system, the mode of propagation, whether it's deflagration or detonation, is controlled essentially by the ignition conditions. So deflagration, for example, are initiated by a mild energy discharge, like a spark, like a match, and so on, while detonation are provoked by shock wave through localized explosion. So we're going to discuss that also later on. An important thing to mention is the deflagration to detonation transition, known as DDT, which is really a subject of current research to understand the cause and what drives this transition is when a flame accelerates as a result of instability, turbulence, obstacle, or whatever, and it accelerates so fast that it eventually develops into a detonation. And that transition is what is known as DDT, and it's, as I said, it's still a subject to understanding. So with this, I finished this section, and the next one is really involves certain things that I'm sure that many of you know, and so I am going to walk through it a little bit fast, skipping certain things. The first item is discussing stoichiometry. So we saw that if a given reaction is expressed in this form, that there is a relation between the change in number of moles in a certain reaction between two species I and J, which is given by this relation. And if you express in terms of mass, then the Ni is replaced by mass divided by molecular weight, so you can write it this way, or you can rewrite in terms of the mass fraction. So essentially, this is the relation that I want to emphasize or to start with. So it's the change in Yi divided by the change in moles times the molecular weight between two species are related to each other. Now, if you take say, I'm not sure I need all this. You can read it later. Essentially, I want to focus on a global reaction that I can write as fuel plus oxidizer go to product. So for example, if it was this hydrocarbon written here, then the fuel is the specific hydrocarbon, say, that I chose with M and N. The oxidizer can be oxygen or air, and then the product is whatever the species that are produced there, right? So I will use nu F and nu O for the fuel and oxidizer, and then whatever I need, I will use the subscript for the other species. And since fuel and oxidizer are always reactant, then I will avoid the prime because it's obvious that they are oxidizers, that they are reactants. Now the expression that we had just in the previous slide, this relation, can now be written. Oh, what am I doing? Oh. Okay, sorry. I pressed the wrong button and disappeared. So we can write it for the fuel and oxidizer. So if this is the fuel and oxidizer, the double prime is 0, so it's NF, nu F, and nu O. So this is essentially what's written here, right? And we can integrate this from the unburned end to the burn end, and to some intermediate state. So we're integrating this relation that was written previously from the unburned state to some state, right? And so you get YF minus YF unburned, U represent the unburned, divided by this factor, is equal to YO minus YO unburned divided by this factor, okay? Now, we refer to a stoichiometric mixture, one in which both the fuel and oxidizer are completely consumed. And so if they are completely consumed, the end state will be that YF is 0 and YO is 0. So there is a ratio here, YFU to YOU is equal to nu FWF divided by nu OWO, right? And this is essentially, so the ratio, the fuel to oxidizer ratio at stoichiometric condition is given by this ratio, which is essentially the mass-weighted stoichiometric ratio of the oxidizer to the fuel, okay? And now we define an equivalence ratio, which is given YF over YO, in other words, given a certain mixture, the ratio of the fuel to oxidizer divided by the same ratio at stoichiometry, which is from the previous slide, it's equal to this, right? So phi is essentially expressed as nu, which is the mass-weighted stoichiometric ratio, multiplied by the ratio of the mass of the fuel divided by the oxidizer. So clearly, if you are at stoichiometry, then this is equal to 1 over nu, and so phi is 1. Okay? So stoichiometry condition correspond to phi equal to 1, and as you know, lean for phi less than 1, and phi bigger than 1 correspond to a rich mixture. And some people, or in practice, sometimes people, when it's combustion is in air, people define this instead of the ratio of fuel to oxidizer, define fuel to air, but it's equivalently the same thing, it's just slightly different number. That I don't need, that I don't need. Now, here I want to go to the definition of adiabatic flame temperature. And the only reason I'm doing this quickly, it's because I want you to see that actually the simplified expression that we are going to use later in the analysis when we make a lot of simplifications come exactly from the same relation that you can do the more general case. Okay, there are sub-case of this. So adiabatic flame temperature is defined that if you take a given combustible mixture and you let it approach equilibrium under isobaric condition, okay, in other words, under constant pressure condition, and it's an adiabatic process, no heat is lost to the environment, then the temperature that it's reached when you reach equilibrium, it's called the adiabatic flame temperature. And the notation is TA. So since it's isobaric and adiabatic, then the change in enthalpy must be 0. The H is 0. So H unburned is equal to H burned, right? And H can be written, since it's H of the mixture on the unburned end, so it's the sum of the Yi unburned Hi, and similarly for the burned state. And the Hi are the enthalpies, which can be written as the enthalpy of formation plus the sensible enthalpies. Now, of course, the Cp, it's a Cp of the mixture of the unburned mixture, U. And the Cp here is the Cp of the burned mixture, right? So it's a summation of the Cpi, Yi in that state, whether it's unburned or burned. Okay, so this is exactly the same relation that was written here after moving this term to the left-hand side and this term to the right-hand side. So if you do that, you get that the difference here between Yi unburned minus burned multiplied by the enthalpy of formation is the difference between the sensible enthalpies. This is from the reference state to burned minus from the reference state to unburned, okay? And as I just said a minute ago, CPU and CPB are the specific heat of the unburned mixture or the specific heat of the burned mixture. Okay, now remember the relation that we had a few minutes ago about for a one-step global reaction, that we said that there is a relation between the mass fraction of species I and species J that depend on the number of moles that went into the reaction and the molecular weight. So this relation we have seen before. Let's apply it such that J, one of the two, J is the fuel, okay? So then dyi is equal, divided by this factor, is dy fuel, and only here is nu F, which is the nu prime, right? And if we now integrate this from the unburned to the burned state, then the difference here will be Yi unburned minus Yi burned. The denominator is brought here in the numerator on the other side of the equation. And the integration of this will be Y fuel burned minus Y fuel unburned. Okay? Now I think I have copied this on the next transparency. Not quite. What I have done is use this expression to replace what you have on the left-hand side of the enthalpies equality, right? The energy equation, this expression here. Okay, so when you replace it, what you get is, well, you get certain, well, here it is, no. Here it is. So I am substituting this in top here, and so you can see that the part with the I is going to be these guys, you know, multiplying the HI naught, okay, which is here, and that's exactly the difference between the enthalpy of formation of the product and reactant, which is the heat release, right? So the left-hand side is essentially the heat release multiplied by this difference, and the right-hand side is those two integrals, which I moved, I changed sides, okay, in writing them. Okay. Now, just for simplicity, let's assume that the reference, if not, then you have an extra integral in that expression, which is known, so it's not a problem. But I can assume that the reference temperature is exactly T unburned. Just simplify the algebra. So if I assume that, then I have an integral here from Tu to Tb and from Tu to Tu. So this one is gone, and so that's the only thing left, which is here. And what's on this side, it's essentially written here. But in addition, what I have assumed in writing what's in the box is that the combustion is complete. When combustion is complete, the fuel is totally consumed. So essentially, I'm assuming that I have a lean system in which among the fuel and oxide, it's a fuel that is being consumed. So if the fuel is consumed, then you get this relation that tells you that the integral of the specific heat of the burn mixture is equal to this relation that depend on the heat release, right? So now, in principle, I can rewrite this expression, and those are the few details here which I will not go through. Instead of mass base, molar base. So the capital C, it's the same as the little c, but on molar base. And what this does is that the right-hand side become only Q. Okay, in other words, this factor is the one that makes the conversion. So what you have is this simple relation that tells you that the change in the integral of the specific heat of the mixture from the unburned to the adiabatic flame temperature is equal to Q. Well, that's essentially an equation to compute the adiabatic flame temperature. It's just that this expression is in a way implicit because you don't know TA a priori, and so you don't know how to, and those CP depend on temperature. So the way to solve this is by iteration. So that's what you see in this example. So suppose that you take methane with the proportion between methane and air, it's 1 to 15, and in number of moles. And if you determine the number of moles, if you balance this equation, you obtain that B1 is 1, B2 is 2, B3 is 11.85, and so on. And you want to compute the adiabatic temperature from here, right? So Q is equal to the heat. Well, we know how to compute Q because it's a difference between the heat of formation of the reactant and product. So we look at tables, and it come up to be 191. And now we want to compute the left-hand side. Well, the left-hand side is the specific heat of the burn on the burn side. So if on the burn side, then it will involve all these species, 1, 2, 3, and 4. So it will involve 1, 2, 3, and 4 multiplied by the number of moles, right? Remember, this is on molar basis now. But this CP depends on temperature. So if I know the temperature, I can integrate, if I know the adiabatic temperature, which is the end, the upper limit, then I can integrate this using, for example, the NASA polynomial, right, that I know, that tell me the dependence on T. So I make a guess. I start, let's say, with 2000 K for the adiabatic temperature, and I compute the left-hand side. Once I know the upper limit, then I can compute this because all these are polynomial. You can integrate them and evaluate the left-hand side. Of course, there are today software that does it for you, but it's important to understand where it comes from, and that's why I go through this. And so you make a guess, and then you compute the left-hand side. You see it's 231, which is bigger than 191. Well, then you have to decrease TA. So you decrease it to 1700, you get, it's a little less, and then you keep on iterating until you converge. And the converging gives you a value of adiabatic temperature of 1732 Kelvin. Of course, this is a bit too big in reality because in calculating things here, I did not assume that there is some dissociation of the product. And you can include this. So, for example, if you include the following species in the product, then if you include, let's say, CO2 and water, then it well, that you don't have to include. That's originally there, right? So if you include, in addition, CO, then you see it drops a bit. If you add O, it will drop a little more. And if you include all these, the dissociation of all these products, it will go all the way to 1725. And then later, if you include more species, it really doesn't change by much. So you know, just to show you the dependence on these things. So anyway, so this is the basically to calculate the adiabatic flame temperature. For me, since I am going to use the more simplified models from now on, let's say to discuss laminar flame structure and so on, I want to get a simple expression. And the simple expression is obtained if I assume that all the CP is independent of temperature. If I take an average value for the CP. So if we go back to that same relation that we have analyzed before, that can be used to compute things in a more precise and accurate way, if you assume that Cp is a constant, then you pull out of the integral, and that integral gives you Ta minus Tu. So then Ta minus Tu, Cp goes in the denominator here, and so you obtain that Ta is Tu plus essentially the heat release per unit mass that react. And that is the adiabatic flame temperature. Now remember that when I started, I said let's assume it's a lean mixture where YF vanish, right? Well, if it was a rich mixture where YO vanish, not YF, then clearly you're going to get a similar relation, but it's going to depend on YOU instead of YFU, right? And if you are exactly at stoichiometry, the two relations are the same because YFU divided by nu FWF, it's exactly equal to YOU divided by nu OWO, which is by definition stoichiometric conditions, and so the two relations are the same. So in general, if you plot, let's say, the flame temperature, the adiabatic temperature, as a function of the equivalence ratio, you are going to obtain that, of course, it peaks at the stoichiometry, and it's lower on the lean side, lower on the rich side. And here is a table that shows you typical values in the range of, I don't know, 2,000 to 3,000, something like that. And here are some curves calculated, taken from Ed Lowe's book, calculated for different fuels. And I didn't want to go through this, but I nevertheless will go through it very quickly. What we have done so far, we calculated the adiabatic flame temperature, which, as I said, defined as for adiabatic condition, right, and under isobaric, right, under constant pressure condition. Suppose we have a mixture in a closed bomb, and so the volume is constant, the pressure can change, and we let it go to, it burn to all the way to equilibrium. The question is what the temperature that it reached. Would it be lower or higher than the adiabatic flame temperature? Because it's not at the constant pressure. And so that's what I just want to quickly note here. If it's in a closed vessel under constant volume, not constant pressure, then it is the internal energy that is conserved. So you have to equate the internal energy of the unburned gas to the internal energy of the burned gas. And the algebra is a little different, and it leads to the expression which is in this box in general. But if you specify it for a constant specific heat, then it's simplified to the two expressions at the bottom. This is for lean, this is for rich. They may look the same, but there's one small difference than the expression before. That's a CV, not a CP. Okay? So the flame temperature that you reach under constant volume condition, it's going to be the heat release divided by CV, not CP. And since CV is smaller than CP, then the temperature is higher. Okay? And so the temperature that you will reach will be, that's why I call it T burn, because it's not T adiabatic normally used. It's not the adiabatic flame temperature, it's the temperature which is higher. So it's like the adiabatic temperature for constant volume condition. Okay, I think that's the last, oh no, then, okay. So the next few items are quite important, but they are general, and so I may skip few things as I go along. We have 10 minutes, right? We finished 15, is that correct? Okay. First is to say that in most of the discussion that will follow, we are going to use a one-step described as fuel plus oxidizer go to product. And so the reaction rate will be written in this form. Here is the B, the pre-exponential factor. I have neglected the weak temperature dependence, T to the alpha, yeah? And then it's the concentration. The concentration can be written as rho y divided by W, so for the fuel or for the oxidizer, since there are only two reactants, then it's the product of those two. And when I will use reaction order different than 1, then I will use NF and NO, which can be in general any number, which are empirically determined, not necessarily the stoichiometric coefficient, right? We talked about that yesterday. And then here is the exponential dependence with the Arrhenius exponential, the activation energy. So the equations are going to be as such. Here we will also generally treat the coefficient constant in most of the discussion. I will tell you sometimes some generalization can be done if you allow them to be temperature dependent, but in general it's more convenient to for understanding things to keep them constant. It makes the algebra simpler. So these are constant, so I can pull them outside of the Laplacian terms usually, right? So mu times this quantity, and then rho di times Laplacian of yi, lambda Laplacian of t, okay? So those are constant. And then since there are only two reactants, fuel and oxidizer, then there are only two such equation, okay? And for the reactant, there will be a minus here because the nu double prime is 0, so and the nu I will be either nu F or nu O, okay? So this is, and omega is the reaction rate, which is given here. So these are the equations that you really should focus on, that we will discuss in the next lecture and in few more later on. Occasionally, we may look at a simpler system than fuel and oxidizer, but I will tell you about it when we get there. It's convenient to take this equation and to write them in a non-dimensional form to get a sense of the magnitude of the different terms, at least. But also, in analysis, it's convenient to work with dimensionless equation rather than dimensional equation. And so, to write things in dimensionless way, it's really not a unique, there is no a unique way. It depends how you choose your scales, and sometimes there is one choice, sometimes there are multiple choice. So, for example, here we are going to choose the fresh of the unburned gas, P naught, rho naught, T naught, as the reference state, okay? So, in other words, we are going to write every quantity such as, let's say, P as the, so we call P tilde is going to be P divided by P naught. So P tilde is going to be the dimensionless pressure. And of course, we will remove the tilde to avoid complexities in the writing. It's really, as long as we say those are dimensionless equations, it should be clear what we mean by that. So that's not a problem. So that's what we do. Then we have to choose a characteristic velocity, and we're going to choose a velocity v naught, which is at the moment not specified. It's something that characterizes the flow. In some cases, it's clear what it is. In other cases, we have to specify it. So we're in specific problems that we're going to analyze or discuss, we're going to specify the scaling. But I want to do something a bit general first. So, and then there is a length scale that you can choose. Well, there is a different way you can choose a length scale. Remember that this is a representative length scale. It's not something that characterizes exactly, say, a flame or any other problem. It's something that is a representative of that problem, okay? And I will explain that later again. So one possibility is to choose, let's say, if the combustion is some vessel, to choose the size of the vessel. That's a characteristic dimension, right? But another thing is to choose the diffusion length. The diffusion length is the, even that is not unique. There are more than one diffusion length. There is diffusion length based on thermal diffusion, thermal diffusivity, or diffusion lengths based on the mass diffusivity. Well, here I have chosen the diffusion lengths based on thermal diffusivity. Thermal diffusivity is lambda over rho Cp. It has units of centimeters squared per second. So if you divide by the velocity that you have chosen as your characteristic speed, it will give you exactly units of centimeter, right? Centimeters squared per second divided by centimeter per second is centimeter. So that has a unit of centimeter. That's a good choice for a diffusion length. But as I said, one can choose the mass diffusivity, say, of the fuel instead, or the mass diffusivity of the oxidizer instead as your length scale. The equation will look differently, but when you eventually revert them to dimensional equation, they should be identical. Then the time is going to be, well, if you have chosen a velocity and a distance, then the time will be the ratio. So LD over V naught is the time. Similarly, when you choose P naught, rho naught, T naught as your reference state, of course you have to make sure that these satisfy the equation of state. I mean, you cannot choose P naught, rho naught, and T naught totally in an unrelated way. Otherwise, it's a bit inconsistent. So here I made the point that the choice is not unique, and said that, like I wrote on the blackboard, that you write things V tilde is V divided by V naught, then you remove the tilde. So if you now introduce all these scaling in your equations will be dimensionless. In other words, when I see V here, it means V in units of V naught. If I see a P here, it means P in units of P naught, etc. And the equation will involve parameters. And you see there are a few parameters. There is the Mach number here, the Prandtl number here, the Lewis number of the fuel and oxidizer here, and so on. So all these parameters are, in fact, summarized in this relation. So the Mach in this transparency here. The Mach number is the ratio of the gas velocity to the speed of sound. Okay? The Prandtl number is the ratio of the molecular diffusivity to the thermal diffusivity. The way to see that is divide mu by rho and then take the Cp in the denominator and write lambda over rho Cp. So the top is the viscous diffusivity or the kinematic viscosity, and the bottom is the thermal diffusivity. So every dimensionless parameter, it's a ratio of two things, and it tells you the value of the parameter tells you the relative magnitude or the relative importance of these two things in the equation. Then there is the heat release parameter, which it's a heat release divided by the energy, the enthalpy of the mixture, of the fresh mixture, right? So that's the little q, and of course that would appear in the energy equation, the reaction term, right? Then the Prandtl number, by the way, appear here in front of the viscous term, because remember it's the viscous diffusion divided by the thermal diffusion. Now you may ask, where did thermal diffusion come in? Well, remember I used that as my unit length scale, so that's why it's representing the length. If you remember that the length scale is the thermal diffusion, you would, I mean, if you have some knowledge from fluid mechanics, you would remember that normally in front of the viscous term you have an inverse Reynolds number. So where is the Reynolds number here? Well, the Reynolds number, it's exactly the Prandtl number, the reciprocal rather of the Prandtl number. If you choose for the lengths, right, Reynolds number is velocity, density, lengths divided by viscosity, okay? So if you take the lengths, the thermal diffusion lengths, as we did, then that combination turned out to be exactly the reciprocal of the Prandtl number, okay? So they are both, of course, consistent. And other parameters that come in the equation are the Lewis number. We spoke already about the Lewis number. It's essentially the ratio of the thermal diffusivity of the mixture divided by the molecular diffusivity or the mass diffusivity of species I into the bulk, right? So it's written here. And of course, since it depends on the molecular diffusivity of species I, there will be two of them, one for the fuel and one for the oxidizer in our case, okay? And then what other parameters is there? Well, there is one important parameter, which is D here, which is known as the Dam-Kohler number, and it's written here at the bottom. Oh, before that, there is this two parameter here. Nu we have already introduced before. It's the mass-weighted stoichiometric coefficient. And beta naught is the activation energy parameter. So it's E divided by RT naught. Note that I called it beta naught because it depends on the temperature T naught of the fresh mixture, okay? And now the important one before we make a break is the Dam Kohler number. The Dam Kohler number, it's really the parameter that appears in this equation here. After you introduce into the equation all the scaling and you make all these factors 1, 1, whatever comes to be here and so on, and then you get, you know, a whole expression for it. But the expression you get, it's rather simple. It involves two things. It involves a time. In fact, it's a ratio of 2 times. In the numerator, the LD over V naught, which was the time scale that we chose for the problem, but it's based on diffusion, so it's the diffusion time, right? So that's the diffusion time. In the denominator, you have essentially the inverse of the reaction rate constant, which is here it appears into B, right? The pre-exponential. So that's the reaction time. So in fact, the Dam Kohler number is the ratio of the flow time to the reaction time, okay? And so these are the equation in dimensionless form. And let's take a break, and then we will come back to the so-called low Mach number approximation, okay?